Consider the profile of the Earth's surface as shown here. And on the surface of the Earth, let us consider a locality at a specific latitude. Now, from the center of the Earth, draw a line passing through the chosen locality like this. This black line now here is the equatorial plane, and this angle here is the latitude angle. Let us place a horizontal flat plate at the chosen latitude like this. So this horizontal flat plate is the focus of interest, and we need to find out how much insolation falls on this plate. This is kept tangentially to the locality point here, and we need to find what is the normal incidence of solar insolation that is falling on it. So this is the estimate that we need to find out from the solar geometry. Remember that the horizontal plane that we have indicated here doesn't appear horizontal to us, but to a person standing at the locality, this plane will be horizontal and it will also lie on the horizon plane. So this is said, or this is considered as horizontal with respect to a person standing at the locality. Keep that in mind, and then we will now look at the corresponding solar geometry and try to estimate this. This coordinate axis system you are now familiar with. This is a familiar figure. This is the locality of interest, and this is the local centric coordinate system. This is the horizon plane, this yellow plane. This horizon plane can be considered as the horizontal flat plate on which we want to now estimate the amount of insolation falling on it normally. This is the latitude angle phi, this is the azimuth angle, and this is the zenith angle. And this line joining the locality to the center of the sun is the insolation line. Let us now find the insolation on a horizontal flat plate located at the chosen locality here. Now consider a vector like this, which represents the insolation from the sun at that locality. Now that vector is at an angle theta z, zenith angle from the zenith axis. Now this insolation vector can be resolved into components, orthogonal components along all these axes. And these resolved components are something like this. So let us say that I name this as LS, component along the south axis of the local coordinate system, component along the east axis of the local coordinate system, I will call it as LE, and the component along the zenith axis vertically up, I will call it as LZ. Observe that LZ is vertically up, normal to the horizon plane, and therefore if there is a horizontal flat plate placed at the locality, LZ alone is normal to the horizontal flat plate. So it is very important for us to find what is this value of LZ, and that will give us the effective insolation at a place on a horizontal flat plate collector. Now we know that L is the vectorial sum of Ls plus Le and Lz. So they vectorially add up to give you the insolation coming from the sun. Now what are each of these quantities in terms of the parameters of the coordinate system? So Ls, which is along the south axis, is L, and this being theta z, this will be 90 minus theta z, and therefore this would be, projection would be sine theta z, and this projection is cos gamma s. So this would be the value of the insolation vector along the south axis. Likewise, the value of the insolation vector along the east axis will be L sine theta z and sine gamma z, gamma s. And the component of the insolation along the z axis or the zenith axis is nothing but L cos theta z. And this L cos theta z is the important insolation vector, as that is normal to the horizon plane or normal to a horizontal flat plate placed at the locality. So Lz alone is the insolation which is at normal incidence to the horizontal flat plate. Ls and Le are along the horizontal flat plate, so they don't contribute to any effective insolation on the horizontal flat plate. Now how do we estimate L cos theta z? Theta z is the zenith angle, and we don't know that directly, so we should try to estimate theta z from known parameters like latitude angle is known, we know the place, location of the place, time of the day, omega, hour angle, and these are the parameters which are known to us and which we know, which we can measure, and in terms of those we should express this so that we get this Lz with measurable parameters, using measurable parameters. Let me shift the coordinate system to the left. I am also including the earth-centric coordinate system also in this figure. So you see the meridional axis M, the east of the meridian, and the polar axis P. And I have included the insolation line also joining the center of the earth to the distant sun. As the sun is very far from the earth, we can consider the insolation lines as parallel in either of the coordinate system. And in this earth-centric coordinate system, let us see how the insolation L gets resolved into. Consider an insolation vector L like this, and this insolation vector can get resolved into three orthogonal components along the meridional axis, along the east of the meridian, and the polar axis, like this. So let us say we have along the meridional axis, it gets resolved as Lm, and along the east of the meridian axis as another insolation vector, and we'll call it as Le, and one along the polar axis we shall call it as Lp. And L, the insolation vector, is the vectorial sum of Lm along the meridional axis, Le along the east of the meridian axis, plus Lp along the polar axis. Now from this coordinate system we can easily deduce that Lm equals L cos of this angle delta and cos of omega would be along Lm. So clearly you can write it as L cos delta and 2 cos omega. And along the east of the meridian LE, we can write it as L cos delta sine omega. So you will get it as cos delta sine omega. And LP along the polar axis would be L cos of this angle nothing but 90 minus delta. So you will have LP along the polar axis as L sine delta. Here the resolved components are in terms of delta and omega. Delta is the declination, omega is the hour angle. Both delta and omega hour angle are deducible, can be determined knowing the time of the day and time of the year. We can calculate that, and we know how to calculate that. Therefore, Lm, Le, Lp can be easily determined. We had also resolved this insolation vector along the local coordinate system, and we are interested in the normal incidence to the horizontal plane placed at the locality. How do we make use of these resolved components along with the resolved component of the insolation at the local centric coordinate system? Because the local centric coordinate system and the earth centric coordinate system have different origins. So one assumption that we can make here is that the radius of the earth is very small compared to the distance from the sun. So in addition to the insolation lines being parallel, they can be merged. So which means we push the horizon plane straight down to the center of the earth and merge the origins of the local centric coordinate system and the earth centric coordinate system. Then we will be able to relate these resolved components obtained from the earth centric coordinate system with the resolved components of the local centric coordinate system and make the relationship. This assumption is valid in the sense that the radius of the earth is very small compared to the distance from the sun, and without loss of generality we can push this coordinate system and make it merge to the center of the earth. Let me give you a 3D visualization of merging the two coordinate systems such that they both have the same origins. So what I am going to do is take this local centric coordinate system and try to push it down to the center of the earth such that this origin and this origin are the same. First, what I will do is I will make the horizon plane a bit bigger such that when I push it down, it will stick out of the globe so that we will be able to recognize where the horizon plane is and how it is oriented. And also I will make the coordinate axis of the local centric system a bit longer so that when we push it down to the center of the earth, this will still project out. Observe now that I have made the horizon plane bigger, much bigger. I have increased the lengths of the south axis on the horizon plane and the east axis on the horizon plane. Now we will push this whole system down to the center of the earth. When you push the horizon plane down such that the origins meet and merge at the center of the earth, you will see that the insolation line also merges together. The east on the horizon plane is same as the east of the meridian. So both the axes east merge together. This is the south axis on the horizon plane. So if you rotate, you will see that the horizon plane cuts through the center, and you'll be able to visualize it much better in this angle. See that the south axis, the east axis coming in like this, they have the origin at this point at the center of the earth. Both earth centric and local centric origins are same. And you see this was the zenith axis, continues to be the zenith axis, normal to the horizon plane. So if one positions on the east axis and looks in this direction, so it will appear as though like this, and we are standing on the east axis, so it looks like a line here, and you see the horizon plane in this fashion here, and this is the insolation line. You have the zenith axis, the polar axis is right up, the meridional axis is along this line. The east of the horizon and the east of the meridional axis will appear like a point here. It's in fact coming out of the screen. Coming back to the 2D graphics, let us view standing here. Let us view in this direction. So when you view in this direction, we saw the visualization in 3D, and let us try to capture it in 2D. You will see, of course, this vertical axis, P, the polar axis, like this. And then viewing from this direction, the equatorial plane will cut across as the equatorial plane, and the horizon plane cuts across, and we saw that cuts across through the origin, because we have made the origins of the two coordinate system the same, and the horizon plane cutting through the origin will look like this from this view direction. And from this view direction we will see this line, the meridional axis. It will appear here. This point would be the two easts, the east of the meridian and the east on the horizon plane, the meridional axis. This is the zenith axis. This zenith axis, right from the origin, it continues up normal to the horizon plane, and that is Z. This angle would be phi, the latitude, and this is what you would see if you are standing on this side. That is, if you are standing on this side and facing towards the center of the earth, you would see this kind of a profile of the coordinate axis. In this way, if the horizon plane and the equatorial plane are merged like this, with the two coordinate systems, local and equatorial coordinate systems merged together, we have this two merged coordinate systems in this fashion, and the variables like the insolations in the earth centric coordinate system and the local centric coordinate systems can be related by this angle phi, and that is what we now propose to do, so that we bring in a relationship of the insolation such that it is along the zenith axis in terms of the latitude, the hour angle, and the declination. We have seen that the insolation vector L resolved into the three orthogonal coordinates of the local centric coordinate system. We have seen L resolved into LS along the south axis, LE along the east axis, and LZ along the zenith axis, and it is of interest for us to find out this insolation vector along the zenith axis, which is L cos theta Z, the zenith angle. We have also seen the insolation vector being resolved along three orthogonal axes of the earth centric coordinate system, and then we have the LM along the meridional axis, LE along the east of the meridian axis, and LP along the polar axis, given in this fashion as a function of delta declination and omega. Now let me put down the two sets of equation. So from the local centric coordinate system, we have the insolation L, which is a vectorial sum of LS, LE, and LZ. And from the earth centric coordinate system, we have L as a vectorial sum of LM, LE, and LP, L polar. And we have also seen that if we stand on the east axis, both the east from both the coordinate system, east of the meridian and also east on the horizon plane. So you will see that the axis profiles are like this, and then we have merged the horizon plane 0 origin and the equatorial plane origin this fashion. We can now represent or obtain the insolation along the zenith axis in terms of the equatorial plane or the earth centric coordinate system parameters. Now looking at the figure here, LZ is along the zenith axis, which is orthogonal to the horizon plane, and LZ can be resolved into LM on the earth centric coordinate system and also LP on the earth centric coordinate system polar axis. So LM and LP earth centric coordinate system vectors can form and give LZ the zenith axis vector, which is what we want. So let us say LZ is equal to LM cos phi, phi being the latitude angle here, and also LP sin phi. So the vectorial sum of LM cos phi and LP sin phi will result in LZ. Now in each of their respective coordinate systems, we have written down what is LZ and what is LM and LP. So substituting, we find L cos theta Z, this is the zenith angle, equals L cos delta cos omega. L cos delta cos omega is LM, which we have substituted here into cos phi, plus LP, which is L sin delta, into sin phi. So this is the relationship that would come out. So cos theta z, which is the cos of the zenith angle, can be expressed wholly in terms of declination, hour angle, phi, the parameters related to the earth-centric coordinate system. To summarize, consider a portion of the earth surface, and on the surface there is a locality point as shown here, and at that locality point I am placing a horizontal flat plate collector, and our interest is to see how much amount of insulation falls on it perpendicularly, normal to that surface. So it is of interest to us that along the z-axis, what is the amount of insulation Lz that is falling on this flat plate collector, and that we saw from this equation. Lz is nothing but L cos theta z, where theta z is the zenith angle. But we don't know the zenith angle. We know other parameters in the earth-centric coordinates like the declination, the hour angle, latitude and such, and therefore we know that now Lz can be written as L sine delta sine phi plus cos delta cos phi cos omega. So this would be the insulation that is falling on a horizontal flat plate placed at a locality located on the latitude phi. All these parameters are determinable knowing the time of the day, time of the year and the latitude. Now this L is called the extraterrestrial insolation in kilowatt per meter square. This is basically the insolation at the Earth's outermost atmosphere, that is outside the Earth's outermost atmosphere. If you place a 1 meter by 1 meter square plate, the amount of insulation falling on that is this L, which is very close to the solar constant of 1.37 kilowatt per meter square. However, it will vary from the solar constant depending upon the time of the year. We will discuss that shortly, but keep in mind that this is outside the Earth's atmosphere.